In this video, we want to start talking about the dimension of a vector space. And when we say dimension, up to this point, we've really been talking about the dimensions of a matrix. So for instance, given a matrix A like this one, we would say that it's a 3x4 matrix, or it has dimensions 3x4, since it has 3 rows and 4 columns. At this point though, dimensionality is actually something totally different than the dimensions of a matrix. We still say that the dimensions of the matrix are 3x4, but the dimensionality of the matrix, or the dimensionality of a vector space, is going to be an entirely different concept. When we talk about dimensionality, or the dimension of a vector space, we say that the dimension of a vector space is the number of basis vectors that are required to span the space. So if we only need one vector to span a particular space or subspace, the dimension of that space would be 1. If we say that we need 2 basis vectors to span the space, the dimension would be 2. So to give some examples of this, let's talk about the dimensionality of the null space and column space of a matrix. Let's use the matrix A, and the first thing we'll do is quickly put this matrix into reduced row echelon form, because that's going to allow us to get the dimension of the null and column spaces directly from the matrix. So if we put this into reduced row echelon form, let's do this quickly and divide through the first row by 2. When we divide through the first row by 2, we get 1, 0, 2, -1. Then let's go ahead and take the second row minus this new first row to zero out this 2, 1 position, this 1 right here. So if we say 1 minus 1, we get 0. 3 minus 0 gives us 3. -1 minus 2 gives us a -3. And 0 minus a -1 is 0 plus 1, or 1. And then we have 0, -2, 1, and 1. Now let's divide through the second row by 3 in order to get a 1 in this pivot position here. So 0 divided by 3 is 0. We'll get 1, -1, and 1/3. And then for the third row here, let's take 2 of this second row and add it to the third row. So we'll get a 0 here. And then 2 times 1 is 2, plus a -2 is 0. 2 times -1 is a -2, plus 1 is a -1. And then 2 times 1/3 is 2/3, plus 1 is 5/3. Now let's multiply through the third row by -1 to get a positive 1 in the pivot position here. That'll give us a positive 1 there and a -5/3 here. Then if for the first row, we take the first row minus 2 times the third row, we'll get 1, 0. 2 minus 2 times 1 is 2 minus 2, or 0. -1 minus 2 times a -5/3 is -1 minus a -10/3, or -1 plus 10/3. We could say that that's -3/3 plus 10/3 is a positive 7/3. And then for the second row, we'll add together the second and third rows. So we'll get 0 plus 0 is 0, 1 plus 0 is 1, -1 plus 1 is 0, and 1/3 plus a -5/3, or 1/3 minus 5/3 is a -4/3, and then 0, 0, 1, and -5/3. So now that we've got this into reduced row echelon form, let's go ahead and put this into proper matrix form again. So we have 1, 0, 0, and 7/3. We have 0, 1, 0, and -4/3, and 0, 0, 1, and -5/3. Now, when we talk about the dimension of the null space of a matrix, or specifically we'll look at the dimension of this null space of matrix A, the dimension of the null space is called the nullity. So if you hear that word nullity, that means the dimension of the null space. And we can either write that as the dimension, let's say we do have the matrix A like this one, the dimension of the null space of A, or just as the nullity of A like this. These two things mean the same thing, the dimension of the null space of A or the nullity of A. Either way, that's the dimension of the null space of the matrix A. And that's always given by the number of free columns in the matrix when we have the matrix in reduced row echelon form. So remember, a matrix like this, we would often associate these columns with variables. So we would maybe say x1, x2, x3, and then here, x4. And because we have pivot entries in the first 3 columns, those are pivot columns, whereas the 4th column here is a free column. So in this case, the nullity of the matrix A is 1 because there's 1 free column in the matrix. That means we only need 1 column in order to span the null space of A. And that makes sense because if we were figuring out the null space of this matrix, we would end up with this solution here. We would have x1, x2, x3, and x4. And we've already looked at this. We know how to find the null space. So we would take a couple steps. We would get here, and we would have x4, and it would look like this. We would have -7/3. We would have +4/3. We would have +5/3, and then we would have 1. And this would be the basis vector for the null space. In other words, we would say that the null space of A is given by the span of this vector right here, the span of that vector. So we only need 1 vector to span the null space of A. We only need 1 vector to form the basis for the null space, which means the nullity of the matrix is equal to 1. Now, when it comes to talking about the dimension of the column space, so we'll say here, the dimension of the column space, we call that the rank of the matrix, and we write that as either the dimension of the column space of A or as the rank of A. And as you might guess, the rank of A is always given by the number of pivot columns or the number of pivot entries that we have in the matrix. And so in this case, for this particular matrix A, we have 3 pivot columns, and so the rank is going to be equal to 3 for this particular matrix. That means we need 3 vectors to form the basis for the column space of A, or we need 3 vectors to span the column space. We can get those 3 vectors from the original matrix if we want to. So we could say that the column space of A is spanned by simply the first 3 columns of A. So we'd come up here and we'd grab these 3 columns. These are the 3 columns. We would outline them like this, but we'd have these 3 column vectors, and we could say that these 3 vectors span the column space of A or form the basis for the column space of A. And that makes sense because when we put the matrix A into reduced row echelon form, we were able to get pivot entries in these first 3 columns here, which tells us that we can use the first 3 columns of the original matrix to span the column space. The only other thing you want to notice here is that when we put a matrix into reduced row echelon form, every column is either going to be a pivot column or a free column. There's no other possibility for each column of a matrix. It's either pivot or free, which means that the number of columns in the matrix is given by the sum of the nullity and the rank. So if I say that I have an m by n matrix, so if matrix A is m by n, and in this case we have 3 rows and 4 columns, so it's 3 by 4. Oftentimes we'll just call the rank R, and so we could say that the dimension of the column space is given by R, and then because we have n columns, oftentimes we'll say that the dimension of the null space, the nullity, so the dimension of the null space, is given by n minus R, where we take the number of columns in the matrix and we subtract out the rank of the matrix. Because if I say there's 4 columns in the matrix, 3 of them are pivot columns such that the rank is 3, then I know that the nullity is simply the number of columns 4 minus the rank 3, or 1. So that is the dimensionality of a vector space, and more specifically, the dimension of the null space, the nullity, and the dimension of the column space, or the rank.